Assalamu alaikum, ladies and gentlemen. Welcome back to another live stream. So this is part 2 of my Vulkan tutorial series, my latest modern Vulkan tutorial series. So let me share the stream in my Discord server. Please join my Discord server. You can find the link down in the description. Loop Preliminary, hello. Welcome back to the stream. Okay, so we're up. Alright, let me grab the chat and we're gonna start. Alright, cool. Okay, so I have published the code from the previous video. If you don't know, this is part 2 of this tutorial series. So of course we're using Vulkan HPP RAII. Alright, so there's gonna be branches for each practical project we do. Basically I'm basically making projects using Vulkan and C++ and explaining everything along the way. So the first project I decided to make is just a simple colored window, pretty much. I've shown you all the steps you need to do that. And after we're done with that, next step it's going to be a textured window, which is basically going to be a window with a texture on it. And this is what we're going to implement in today's video. We're going to learn about VMA, the VulkanMemoryAllocator, which is a very efficient library to allocate memory in the GPU. Of course, using the Vulkan API. You're also going to be learning about how to set up SDL image and also how to use it along with Vulkan, hopefully. Other than that, we're first of all in this stream, we're actually gonna continue improving or improve the colored window demo and fix a few things pretty much. So yeah, that's basically it. Is there any questions before we start? And please start this repo so it can get promoted to more people out there, pretty much. Other than that, I think we should be good to start. By the way, there's also GitHub workflows here that I made. AI really helped me set up this because I had some problems with GCC and not being the latest version, for example, and shit. So it really helped me with that. And right now we're actually having actions. And as you can see, where is it? I think this one. Alright, there we go. So as you can see, we have Ubuntu latest release CL. Windows release CL. We have also what is it? This. So Ubuntu latest release GCC, Ubuntu latest release Clang, and Windows latest release CL. So basically MSVC, and both actually how much time they take? Hold on. So Ubuntu takes around, well, all of them takes from, let's say, 2 minutes to 3 minutes basically so far. Alright, so let's get to coding. I think let's get into coding already. Alright, cool. So the first thing that I'd like to actually show you is the fact that you can actually disable and enable some SDL subsystems to make your output executable much smaller and also decrease the compile time, although arguably not very big impact, but well, it is working, I guess. But yeah, alright, so I have two profiles here, release and debug, nothing fancy. So here in the cache variables you could see the SDL flags right here. And in fact, even in here in the CMake, if you see this, there is some subsystems here. All of these are on. Well, I have actually GPU and render. Actually, these should be on by default, but it's just because I had them on before the cache wasn't flushed, the CMake cache. and they should be on by default. But basically we don't actually need SDL GPU and SDL render subsystem, which are used like if you want to actually use the SDL render. But in our case, we're making our own Vulkan render, so we don't need them at all. And they're quite big, not too big, like let's say around, you're gonna shave around 0.5 megabyte, you know, and of course you're gonna decrease the compile time a bit. But other than that, let's get going, I think. So how you want to do that? Well, set SDL, let's see, render off cache bool force, and same thing with the other one, SDL GPU off cache bool force. You could also like remove the other ones, like let's say what is it called, SDL audio, but honestly, for example, SDL audio isn't that big, and honestly all the other subsystems aren't that big. But like if you remove all of them though, in my test case at least, I almost got away with shaving off 1 whole megabyte, you know. But yeah, honestly I'm not gonna go that path. Another subsystem that is reasonably big, though not as big as render, though less big than SDL GPU, which is SDL joystick. I think, is it joystick? Hold on, let me see here. What is it called? Yeah, joystick. And of course, if you disable joystick, you should also disable haptic, which depends on it. Otherwise, CMake would fail to actually generate. So if you don't want, you know, joystick support, then you could also remove that, and make sure to remove SDL haptic too. And that's basically it. For the other ones, doesn't really matter that much. They're not as big, you know. But if you really want to go that crazy, you can. But anyways, let me just reload this CMake. And now let's see if that actually. Hello, Theo Paris. Welcome to the live stream. How's it going, man? Alright, let's see. So as you can see right now, the joystick and the haptic subsystems are also off, which is great. Perfect. Now let's try to actually run this. And there we go. Perfect. Another tool that I wanted to share with you is NVIDIA Insight graphics. If you have an NVIDIA card, if you have an AMD or Intel, they also have their own tools, but I don't, so I can't cover them. You may want to look if there is some tutorial out there. But I just wanted to show NVIDIA Insight real quick. And show you how much information it can actually give you. So where is it? Hold on. Insight graphics. You could of course install it real quick. Just, you know, search on the web and you're gonna find how to install it. So Insight graphics. Oh, I almost forgot. Make sure to actually run this in oopsies. In run as administrator, basically. Otherwise it won't give you all the metrics you need for the GPU. Okay, so let's start by just debugging our own application that we have made here. It's nothing fancy, so let me just build a release application real quick here. Shouldn't take that long, I guess. And there we go. Perfect. Now let's just copy the path here. So how are we gonna do that? Let's see. Copy path reference, absolute path. Let's come here, start activity, and then we could basically paste it here. You could set the working directory if that's needed. Other than that, you could choose between these ones. Like there's the frame debugger, generate C++ capture, GPU trace profiler, and shader debugger beta, and system trace. So the frame debugger is like render doc. You just get to debug one frame, and that's basically it. And it's more graphics oriented, like you see the shaders, you see the images, etc, etc. Generate C++ captures. It allows you to generate a replay, like for example, if there is a bug on your machine, on your GPU, you could like generate a C++ capture of that bug and give it to someone else that they can run of that particular frame or whichever. But anyways, GPU, wa alaikum assalam, Sihan Kinar, welcome to the live stream. Oh, thank you so much. I love your kind words. Okay, so GPU Trace Profiler. This one gives you a lot of information about the GPU stuff that is going on. For today's video, I'm going to show you a bit of Frame Debugger and GPU Trace Profiler. I'm not going to go in depth right now because it's a lot. I only think you have selected the directory path and not the actual executable. Yeah, that is true. And hello to the stream, Nixie Gag. Welcome to the live stream. Let me fix that. Thank you. Open, and there we go. All right. And the other one is Shader Debugger. Honestly, I haven't even tried this yet. System Trace. This one uses nsight systems, as you can see here. Which is more useful for like if you want to debug the interactions between your CPU and GPU. Like it's not just debugging the GPU but also the CPU, like system-wide debugging basically. But yeah, let me just give you a quick look upon this stuff, right? So let's go with the Frame Debugger, and we're gonna go with Vulkan here. And let's launch the Frame Debugger, I think. Or you know what, instead of doing that, let me see if I can, where is that? Apparently there's not. Interesting. Well, let's just launch this. And there we go. And now I'm gonna say F11. There we go. And let's wait for this. Let's see what we got. There we go. All right, cool. And this is what you get. So there's a lot of stuff going on here already. So here you see all the events. You could switch between hierarchical and flat here, but let's just keep it on hierarchical here. So as you can see all the events, all the functions of Vulkan here being called with the CPU milliseconds. I'm not sure why you can't in GPU milliseconds, but for the CPU, there we go. VKQ submit, you could click, and when you click, the event details actually change. You can see the actual return value and all the other parameters, right? So as you can see here, and for example, you could also click on the objects that are referenced. For example, this device, I could click on it, and then it would bring up the objects browser, and then I could see how this device got created, like what is the info of this device. For example, this device, this is how it is created, all the parameters, the enabled extensions, only VKKHR swapchain. And I could even check out the other instances, like other objects in here, and see how they're created. For example, my instance, here we go. Here is the enabled extensions, the swapchain image. Oh yeah, swapchain image. That's interesting. Swapchain, etc, etc. Anyways, what's other than that I want to show? Let's see. Alrighty, let's bring this out of the way, and let's see what we got here. So we got every event here, and for example, this one, if we hover over it, this is VKQ submit. This is VKCMD pipeline barrier, and this is VKCMD clear color image. There we go, and this is the image that is being used here. You could actually see the values red, green, blue, and alpha. You could even see the size of the image in the VRAM, like in the video memory, in the GPU. So in this image is just 2 MB. There we go, the dimensions, image type, the format, etc. You could take this and do that. You could see the history of the pixel. There isn't that much because this is a very simple application. Other than that, is there anything else I want to show? There's also the viewport pipeline render pass, which we're not using in this kind of application right now. But yeah, there isn't that much going on around here for this one. There's all sorts of crazy stuff. So now let's just terminate this and let me show you a more complex example. We're gonna start the activity, and right now we're actually gonna go with VKCube. You can find it in the Vulkan SDK bin, VKCube. Where is it? There we go. So this is an actual Vulkan application demo in the Vulkan SDK. You could open this up and let's see what we get. Let's launch. And right now we could hit F11. And there we go. Now we have a more complex example going on here. You could see all the events again. You could even click here and it would show you which event you're talking about. For example, this is the VKCMD draw function. You could see the actual wireframe even. This is the depth buffer. You could see the context, the objects that are being used. This is the pipeline object. For example, the pipeline object, you could read about it. And also you could see which objects are, like which events are using this object. In this case, only the VKCMD draw. And the usage is read access, right? But yeah, other than that, what else? PXOPS. So there's all these information you could check out. Pipeline. There's also the shader modules, like for example, this is the vertex shader here. We could click on it. I do believe there is a way to actually see the shader code. Weird. Yeah, I'm pretty sure that's the case. Maybe not in this one. But yeah. Now let's say for example this guy right here. We could actually do something like this. And we can see the history of this pixel. But yeah, that's basically it for that one. Nothing too fancy for now. Is there anything I want to cover other than this? I think for now we're fine. Let's cover the other tool now, which is way more interesting than this. Start activity. And let's go with the GPU trace profiler. This one is highly... There's also system trace, but meh. Let's not go crazy. System trace is kind of like GPU trace, but also adds CPU information, CPU tracing information basically. But yeah, there's all sorts of stuff here. But here I'm actually start after, instead of manual trigger, I'm going frame count. I'm gonna start after 0 frames, which means I'm gonna start capturing frames from the start. And limit it to 4 frames, to max frames 4. Only I'm going to basically capture the first 4 frames this way. And let's launch GPU trace. I'm also enabled multi-pass metrics here, and that's basically it. Let's actually try this. And it's gonna go ahead and do that. And doesn't seem to work. Let me actually restart it. Nsight graphics. Okay, and let's start the activity. GPU trace profiler. And let's launch GPU trace. What's going on here? That's strange. Weird. Should work. What about manual trigger? Doesn't work either, huh? Okay, let's try our own application then. I'm not entirely sure what the heck is going on here. Let's copy this guy, absolute path. Let's go back here. Let's paste that in and let's launch GPU trace. Okay, this one seems to be working, though. Let's go back to our frame count now. Max frames, okay. Alright, give me... Why? Oh my god. Okay, now maybe it should work. That was strange. This didn't happen for me before. Data collection not available. I'm very confused right now. Let's try one more time. If this doesn't work, I'm just gonna move on, honestly. Could attack a volcanic, perfect. GPU trace profiler. Launch GPU trace. This is wild. Yeah, I'm not sure why it's not working now. Weird. It was definitely working before the live stream. I'm not sure what's wrong here. But anyways, let's go back into our actual code right now. So what we're gonna do now is, let's see, joystick cap, car, cache. Okay, cool. Now what we need right now is to implement in-flight frames, right? So currently what we have is we have only one in-flight frame, which means that basically if we go to, where is it, render, right? So here, when we prepare one frame, we give it to the GPU to work on it, to render it, right? But then we just wait for the GPU to finish before we start preparing the next frame. So we're just wasting time. What we could instead do, we could have, while the GPU is actually rendering one frame, the CPU could be preparing the second frame and so on. And then afterward, like the CPU would give the second frame to the GPU and then go back and prepare the first frame and so on. And it keeps on going like that. So basically the CPU would always be ahead one frame. While the GPU is rendering one frame, the CPU would be already preparing the second frame, essentially. But yeah, so how we could actually do that? That's a good question. And one other thing though, before I forget, is the instance creation. I forgot one little thing, I believe, about the, well, hold on, create instance. Yeah, instance create info. Yeah, not application version. I meant API version here. So we were using Vulkan 1.0. Alright, so that's one thing. Alright, next up is, let's actually implement right now that thing, right? So struct frame. So instead of having like multiple vectors like this for every single object right here, which is multiple heap allocations, we're gonna have one struct frame which is gonna contain all the resources that belongs to one in-flight frame. So what we're gonna do is vk area I command buffer semaphore. Oh, oops, let's remove that. And render finish semaphore, and we need a fence. And that's basically it. Now instead of having this stuff here, we're gonna have an std vector of frame. Whoops, frames, just like that. Otherwise, instead of this, if we don't want a heap allocation for this too, we could also, like, basically we're gonna have a const expr in flight, well, not auto, let's go I guess with the UN32T in flight frames count. And so this is how much frames we're gonna prepare. Like if this is 2, basically one would, like the GPU would be rendering 1 while we're actually preparing the second in the CPU, and so on. If this is only 1, the CPU would actually wait until the GPU is done with rendering, then do its work, then prepare the second. But yeah, 2 is a good and like ground between 3 and 1. So like 3 is kind of like triple buffering, which may give you more stable and like more FPS. But then again, the more this number is bigger, the more latency of the input, because like in the CPU, you're preparing the frames way before you're actually going to be rendering them into the GPU. The more this number is like, so yeah. So if you really want the lowest latency, you probably want 1, or at the very least 2. If you don't, then you could go 3 or even more, but yeah. Anyway, let's go back to 2 here, and instead of std vector, we could also go with an array frame. So we basically avoid the heap allocation altogether. It's not a really big deal, but this is just something I wanted to show you anyways when it comes to C++. And since this is const expr, it would actually work on an array here. And we don't need a heap allocation. Perfect. Alrighty, so now let's actually... So first of all here, we're gonna need a frame instead. So frame, or actually just say auto const frame. Yeah, and we also need a frame index, right? So frame index UN32T. Be careful though, we don't want to use the swapchain image index here. The swapchain image index and the frame index are way different, right? The frame index is for the actual frame mechanism that we're making between the CPU and the GPU, right? But the swapchain image index, it could be whichever image index for the swapchain, depending on, like, it could give us any index in whatever order, depending on the presentations, like the presentation system, like if it's swapchain, what is it called? Mailbox, or if it's FIFO or other presentation mode, basically. But anyways, for the frame index, let's see the frame index. So here frames, and we're gonna use frame index here, right? And other than that, and at the end of it all, what we're gonna do, we're gonna advance the frame index by 1, and of course we're gonna like modulo in-flight frame count. So basically what's going to happen is it would go 0, 1, 2, and then go back again to 0, 1, 2, as long as, of course, I'm assuming here that the in-flight frame count is equal to 2. So it basically would loop around and start again from 0 whenever it reaches in-flight frame count here, pretty much. So that's cool. All right, so wait for fences. We're going to wait for the fence of the current frame here. So frame dot, and oh, by the way, one other thing here. Let me just go back here for a sec, because we do have a little problem here, which is the fact that right now we're actually using an array, which means we can't actually really initialize it like that. It wouldn't work. Let me see. Let me see if it's gonna give that as an error here, so I can demonstrate it better. There we go. So as you can see, no appropriate default constructor here available. So we can't actually do it like this. If you want this to work, then we should basically make it a CD optional here. We wouldn't need a CD optional if this was a vector instead, and so we dynamically resize the vector. But if you want to use an array, we need a CD optional so we could like default construct them essentially. All right, cool. Now here, frames, frame index, we could basically just dereference the optional because we know the frame would be valid at this point. And here, let's just grab the fence. Why my IDE is bricked right now? This is strange. Let me actually restart my IDE. Start acting up right now. Oh boy. Okay, let's wait for it to load everything. If there's any questions, please let me know. All right, let's see now if this works. Bro, what the heck is happening with the... What? I'm confused. This is very confusing. Let's just try anyways, say frame.fence here. I'm not sure why suddenly it's not working. What the hell? Maybe I should try to just delete this whole thing and try again. That's wild. The last thing I expected to break is my IDE. Pretty crazy stuff. Is the stream fine, by the way? Dropped frame 0. Hopefully, right now I just basically removed the build directory so we can rebuild everything, and hopefully that would fix my editor. Does that work now? My God. Well, maybe let's try some other stuff first and see if it's a problem with that. So instead of init sync objects, we're gonna go with init frames. So here, we create swapchain. We're gonna go with init frames instead, right? And so init frames would basically replace our allocate command buffers call and also our other function of, well, this one and this one. We're gonna do them in one step right now, and you're gonna see why in a second. Init frames. So the first thing, we're gonna allocate command buffers, right? In one batch. Well, here in flight frame count. Instead of one, this time it's gonna be in flight frame count command buffers. We're gonna allocate the commands in one go. What did I remove there? Okay, I see. And then what we're gonna do, generate n. Right. Or honestly, no need. We could just do for loop, simple for loop really. Auto frame. Not really, just say, I guess, size t, and then we're gonna say frames dot in place. Well, really? Yeah, frames I, sorry, dot in place. Yeah, go on, let's see the AI. Frames I dot in place, frame. No need actually for this because we're using in place here, so I guess that makes sense. And let's remove that and that. Yeah, as you can see, the AI isn't perfect. It's good for generating. Let's see what we got. And here we're gonna need to use std move. So we move the ownership of the command buffer from that vector to the frame here. For the semaphore, we're also gonna need a vk semaphore info here. Semaphore info. Well, create info, yeah. And a fence create info 2, perfect. Though the fence, we gotta make sure that it's actually signaled at the start. And there we go. So now we're gonna need the device. We're gonna need the semaphore create info. Perfect. Same thing here. Let's see if the AI could do this. Perfect. And same thing here too. Though apparently it did seem to actually just figure it out on our own here, which is cool. So I guess I could just basically say this. You're talking. Okay, cool. So I could do that, and I could just remove that now. Alright, perfect. I think that should do the trick. So maybe that IntelliSense didn't work there because I had this code bricked. Hopefully right now that would work. Let's see. It still doesn't seem to be doing the trick. What if instead of autoconst I just did it like frame basically and call it a day? What about that? Please don't tell me that was the problem all along. What the heck? Oh my bad, dude. Oh my god. Well, it is actually public. It should be public by default, yeah. That's strange. Frames. Weirdo. Alright, let me just run this and see what are the errors real quick. Oh, missing before. What? Missing a semicolon before. Oh shit. Was that a real problem there? Oh my god. Oh yeah, it was. I mistyped one thing and it broke my whole IntelliSense, my whole IDE. Which is honestly understandable. I mean, it's not like... But yeah, whatever. Anyways, so that works, I guess. This needs the raw handle of the fence, so we need to dereference it from the RAI handle to the raw handle. Okay, so the next thing here is also the same thing. Reset fences, frame.fence. Alright, next up is here the image available semaphore, pretty much. So we're gonna say frame.image available semaphore. Same thing here. Well, actually, fence should be null PTR, yeah. Other than that, we have the command buffer. And honestly, for the command buffer, let's just create a little helper function here called void record command buffer. And let's go. And we're gonna basically take this whole code from here and splice up this function a bit and put it around here. Right. So we're gonna remove this and we're gonna say VKRAI command buffer. Though of course we're only gonna get an address to it, or should I say a reference. It can be made a reference to const, I guess, sure. Is there anything else? Oh, we also need the swapchain image apparently, which is interesting. Okay, sure. Swapchain image. And that's all we need, I guess. Is that the case? How about the swapchain image index? We don't need that? Well, no, we don't. Alright, let's see. Alright, so what we're gonna do is record command buffer, frame.command buffer, and swapchain image here. Perfect. And here we're just gonna say frame.command buffer, here frame.image available semaphore, and here frame.render finished semaphore. Here submit fence frame.fence, and here frame.render finished semaphore. So we're just rewriting most of this stuff, really. Nothing unusual. Is there any other problem? I don't think so. The command can be made static. I mean, okay, I guess for now. Other than that, I think we're good. Record command buffer. We could even splice this up a bit more. We could also convert this to structured binding instead. Oh yeah, this new feature of C++ makes things way nicer, honestly. So we basically destructure this frame struct into its components so we could use them directly as variables here, which is pretty sick. Lovely. Other than that, we could also make the other stuff here as actual, yeah. Interesting. Though, no, I don't want to do that, you know. Image available semaphore. Yeah, no, let's not do that for now. Why? Because you simply... Honestly, right now the swapchain image, we could just directly give it here. Because I want to make this into its own function. Right, so like void begin frame, I guess. Or like, yeah, why not begin frame? Whoops, begin frame. Right, and of course here we're gonna need the frame itself. So frame. Though we're gonna need the image index. Or in fact it's already being used here. So current swapchain image index. We could use it there. And here begin frame. And of course we also want an end frame function. And yeah, it's basically this stuff right here. And that's basically it, I think. Though we could also include this, why not? And other than that, I think right now we could just to simply say end frame. And finally here we're basically submitting the command buffer to the GPU for execution. So submit command buffer. Right, and let's just say void submit command buffer. And here we just need the frame again. And yeah, I think that's basically it. Here we need to pass in the frame. Right. That's pretty sick. So that's our render function right now, you know. Begin frame, record command buffer, submit the command buffer, and then end the frame. As simple as that. As simple as that. Okay, perfect. Let me see if this works now. I had quite a challenge to actually understand this when I was just starting Vulkan, like this in-flight frames crap. And I think one of the big things that was really confusing me is I wasn't really noticing the fact that, wait, let me see where it is. The fact that the fence right here, so like whenever you finish a frame, when you go to wait again, you don't wait for the same frame that you have finished and gave to the GPU for rendering. You actually go one frame over, right? You go to the next frame, to the other frame, and then start preparing that. You start preparing the command buffer for it, etc., while the GPU is still working on the other one. And that's basically how it is. So right now we got in-flight frames done correctly, which is great. Is there any questions so far? I think with that we have basically finished the in-flight frames. like, sorry, the clear color example. No need for this comment here. Record command buffer. This function right here, we could also make it a little bit more clear for readability. Like, yeah, we could do that. So basically, what this pipeline barrier here is essentially just transitioning the image layout. Right, so yeah, let's actually do that. Why not? Static void transition image layout. Let's see if the AI could actually figure this out by itself. So of course you need the command buffer, the image, the format, the old layout, the new layout, huh? You know what? Let me just do it myself, honestly. I don't want to proofread the AI stuff right now. Really not in the mood to do that. So, yeah. Alright, so let's just do it then. So, swapchain image. This should become image instead. And yeah, other than that, we're gonna need the SRC access mask. Well, honestly, the image layout should be a struct. It should contain the SRC access mask. Or let's call it image state, really. Image state. Honestly, you know what? Hold on. Before we do that, let's actually switch to synchronization 2, which is another modern Vulkan extension, which would make for way better synchronization and also gives us structs instead of function arguments, which would make this nicer. All right, let me see. So the first thing is we need to... Alright, so where's the device? We're creating the device here. What the heck? Init the device, yeah. Here we need to add a feature. Device in place. Yeah, so enable sync to, let's see. I think we need not really, yeah, probably. Bruh. Let's see what the heck. What in the world? Oh, there we go. Okay, Vulkan either 1.2 or 1.3. I don't remember. Let's see if synchronization is here. Doesn't really seem like it. How about 1.3? There we go. Synchronization equal to true. And yeah. And we're gonna set the P next to features too. I do remember that Vulkan HPP actually have some sort of mechanism for type safe pnext values, but I'm not sure if I could. Never used it, honestly. Let me see. Vulkan HPP pnext chain. Okay. So apparently you do something like this, right? So let me see if I can do this. Well, actually, so how to enable synchronization sync 2 for device creation. Let me see if I can pull it off. Meh. Using Vulkan HPP. Alright, let's see. Yeah, I don't know. Let's just try ourselves, honestly, at this point. Don't care. Or let's just try this instead. And by the way, I need the Vulkan configurator. My bad. Let's just grab that to make sure we're not doing any problem there. Validation, and let's actually run this up. I had no idea that StructureChain existed. Yeah, it does. There's quite a lot of features there. Designated can only be used to initialize aggregate class types. What the heck? Alright, fine, whichever. You name it. Synchronization to true. Let's see. Oh boy, designated. Features? What features? Well. Can't I just actually do it directly? Yeah, good question. Well, let's just see this and see if we get any validation errors. Validation is on, so whoops, encountered something weird happening there, but anyways. It doesn't seem like it had any problem with it, apparently. So I guess it's good. Anyways, let's just try right now the, well, how about this directly? Like, in fact, why did we even need this then? Strange. Yeah, what if we just do it directly like this? Let's see. Or we could just check out, let's see. Seems about fine to me. Anyways, so next up, let's actually try to use that vk StructureChain instead. StructureChain. What the heck? You know what? Let me search please for how to enable synchronization too. Just to make sure. No, use so basically there is like specific structs only for synchronization 2, but there's also these aggregate structs like Vulkan 1.3, which includes all the features in that version, all the core features in that version. So instead of like having like one struct for every single feature, we could just use that instead. So basically they're doing it this way. Okay, yeah, directly, no need for that crap. Nice, perfect. So I don't really need that stuff. So just like say there we go. But let me actually see how that chain thing works now. Let's see, StructureChain vacate device create info, which we have done here, and then the thing that you want to chain, then you give it the, okay, cool. Let's actually grab this one, and this is like Vulkan 1.3 features. Whoops. Well, actually, let's just remove the redundant stuff there. And then how we could use this chain. Chain.get vacate device. Okay, cool. So here, instead of this, we're going to go with chain.get vacate device create info. Is that it? I think so. Actually, let's remove that. And yeah, that's basically how it's done, I think. Let's try this. And I mean, it seems to be working without any problems there, which is cool. So yeah. All right. I think it also checks the types, like what are the benefits of vacate StructureChain compared to the C API. Less boilerplate, more readability. That's obvious. I think it also checks for if they're valid. Hold on. Okay. Well, anyways, let's just go on. Now let's actually go back to the synchronization stuff. So pipeline barrier. Okay, cool. Now instead of, I'm just gonna comment this out and see if the AI could figure it out on its own. Walaikum salam Woji Girin, welcome to the live stream. Okay, so let's see. Did it figure it out or not? First of all, we don't want to use the KHR because image like synchronization 2 is actually a core feature, core extension in Vulkan 1.3, and we're actually using Vulkan 1.4, so we don't need the KHR there. Core basically means we got promoted into some specific Vulkan version, so we don't actually need to use it as an extension. But anyways, cannot convert our value of type. Okay. The SRC stage mask. So the SRC stage mask we have here is SRC stage mask. Let's see. That's probably transfer, yeah. Well, what the heck? Bro. Really? Bit flags. I think it's probably bit flags. Flag bits too, yeah. Oh boy. Transfer. Okay, cool. That's the one. The SRC access mask. The access mask SRC is this one right here, memory read. So we could just remove that one there. The DST stage mask is also transfer. And the DST access mask is transfer right. SRC stage mask. Okay. Yeah, perfect. The old layout is in the find. Can you just do this, please, so I could see the name? It doesn't actually give me the name, apparently. I guess I just gotta check it out on my own then. Let's see. Yep, new layout, then that stuff. Yep, perfect. So that's good. That's good. All right, now try it. Pipeline barrier 2KHR. What's going on here? Use auto, sure. Well, actually, no. What the heck is happening here? We could just do this. The AI is very strange, honestly. Anyways. And we don't want the KHR version. The dependency info. I see. So vk dependency info. There's quite a lot of stuff going on there. So dependency info. So dependency info dot dependency flags, memory barriers. So we want the image memory barriers only. So what we're gonna do then is set memory barriers. Well, sorry, image memory barriers. Yeah, this one. And we're gonna give it our barrier. And that's basically it. And the dependency info here. And is that enough? Seems about right to me. Seems about right. Perfect. So we have successfully switched from synchronization 1 to synchronization 2 extension. So what's better in this way is the fact that everything is a struct again, just like the usual Vulkan stuff, right? It's all structs, right? The second thing is the fact that it's way more ordered. Like the SRC stuff is ordered with the DST stuff ordered, etc., etc. While here it's all over the place. So yeah. Alright, so let's switch the other stuff now. Or other than that, instead of that, we could also make this into its own little helper function exclusively to just like switch the image state. So let's actually try that. Void transition image layout. And let's see what we're gonna need. The first thing that we're gonna need is the command buffer. That's the first thing. And the second thing is the actual image. Though probably we won't VK RAII image, no? Isn't it? Well, I guess so. Anyways, what else? No, we could actually just go with VK image, fine. We don't need the RAI version here in this function. You would implicitly convert it anyways. So fine. The other thing that we're gonna need is, so these should be customizable, and these should also be customizable. Alrighty. So here, where we're actually gonna create that struct image layout, I guess, where we're gonna have the actual layout. What is it called? Is it called image layout? Yeah. The access flags, the pipeline stage, and yeah. And so we're gonna have a source image layout, so old layout and a new layout basically. And here we're gonna change stuff up a bit. So like the old layout, oops, dot stage mask. Well, pipeline stage flags too, please. And access flags too. Alright. Same thing here. Old layout dot access mask. Well, actually, let's call this access mask instead. And this one, well, and this one, stage mask. Just to have the same naming there, because why not? And this one is the access mask. And same thing here, but this one is for the new layout. Stage mask. And this one is new layout dot access, well, new layout dot access mask. Here old layout dot image layout, and here new layout dot image layout. For the key families, for now I think I'm just gonna pass, or we could just like include them anyways though. We could just include them anyways. Is there an actual typed? I don't think so. Yeah, I don't think so, yeah. So we're just gonna go with U832T Q family. And the Q family index, and we're basically gonna have a default value of VK family ignored. That's basically it. For the image layout, you could also have a default of, well, hold on a second, VK image layout general. We could have that. For the access mask, what is an access mask that is a good default? Good question. Access flag bits 2. So there's enon, host read, memory read, Memory write. Well, we could play it safe and just include both, right? So like memory read and memory write, essentially, I guess. You know what? Let's not overcomplicate crap right now. Let's just keep it as it is, right? Let's just keep it as it is for now. Let's not overcomplicate things. All right, fine. And here, what we're gonna do is old layout dot q family index, and same thing here. Whoops, new layout here. And finally, sub resource range, which I think there's no need for it right now. So anyways, and that's basically it, I believe. So right now we could actually use our new helper function. We only need to give it the command buffer, the image, the old layout, and the new layout. So yeah. So let's actually just comment this out and let's use it. So transition image layout, and let's see if you can figure it out on its own. And yeah, E undefined, E memory read, transfer, key family ignored, transfer DST optimal, transfer right. Yeah, that seems about right to me. So now I could just remove that. Let's make sure that everything is still working fine. Though honestly, for the key family, we could just emit it because it have a key, like a default anyways. So that's good. All right, let's just emit this guy right here. Don't need it. And yeah, there we go. Transfer right. Though to be honest with you, I feel like the stage mask may be nicer as a first or the second argument. Okay. Just nitpicking here, so yeah. All right. Same thing here. And yeah, that's basically it. Now we're gonna do the same exact thing here. Gonna comment this out, let the AI fill in the blanks. So let's see. Whoops, transition. Image layout. And yeah, perfect. So this is the old layout. And this is the new layout. All right. And there we go. That's much nicer now. Now let's actually run this out and make sure everything's still running fine. Other than that, one last thing we should fix is the actual destruction stuff, like the destructor. Other than that, let me make sure that the synchronization layer is not emitting any errors so far. Hopefully not. Yeah, nothing, which is great. Great. Okay, cool. So let's go to the destructure. Where's the destructure here? So app, device wait idle, SDL quit. So why we have that error though? CD optional frame, in flight frame count. Okay, so I'm gonna get back in a second. Alright, back. We don't need the 0 here. Alright, cool. Now the problem that we have is, for whatever reason, we're getting a crash on exit, which is telling me that probably there's something not destructured properly. As you can see here. Let's go with the validation layer. Maybe that could give us some information. Apparently not. Hello, Rio. Long time. Walaikum salam. Alright, we need to figure out where's the culprit here. So our Vulkan code is properly done, but there's something that we added that right now actually results. So this is what we added so far. We have a frame struct, in flight frame count 2, and of course we have our frames instead of all of these vectors right here. We have one array, not even a vector, of frames, and a frame index, of course, to keep track of which frame we are in right now. Instead of allocate command buffers and init sync objects, we have init frames. We basically merge these two functions into one. And then here we have a struct image layout and transition image layout function, which is a helper function which basically does a pipeline barrier. Just a helper function there. And we have our record command buffer function. Our submit command buffer function. Init frames. Chain there. And we fixed the API version thing. Well, I'm not entirely sure, but I guess I'll check that out off camera. For now, I think it is enough. So we could go to the next project, which is actually handling some textures. So, okay. Implement in-flight frames. Flight frames. Whoops. I can't type today. Alright, we're gonna commit this guy. And yeah. Alright, what's next? Next up, we need to add SDL image into the mix, I think. Yeah, let's add SDL image. SDL image, CPM add package, well, SDL3 image. There we go, and let's check out the latest commit of SDL image pretty quick. GitHub. And let's just copy this guy right here. There we go. We need some image right here. Let's just create a folder real quick called assets. Right, and Let's have a folder inside of it called images, I guess. And let me just make a screenshot real quick just to produce an image. And let's copy this path, absolute path. Let's go here, save this guy, go here, save, and there we go. We have this screenshot right here. Rename, let's call this screenshot, and let's try to load it using SDL image. Pretty much. Let's try to run this first. Okay. So now we're gonna actually learn how I could load an image using SDL3 image. And then hopefully, oh yeah, we also need VMA though, for Vulkan memory allocations. So for VMA, VMA GitHub. Well, not that one. Oh my god. There we go, this one. We also need to add this guy. So VMA. CPM add package. GH. Paste that in. And let's grab this commit. And there we go. Now let's append VulkanMemoryAllocator, and we should be good to go. It's taking quite some time to add in SDL image, though I almost forgot. Hold on. I almost forgot. We need to disable something that was causing me problems. And that something is in my GitHub. So let's go to here. Where is my... Yeah, my CMake repo. If you check out my CMake repo, CMake list, I have that in. So yeah, this guy right here, because it's trying to compile AVIF image format, which actually requires Perl and NASM, which not everyone have on their computer. So we're going to, before we add that package, we're gonna disable that AVIF image format, and we should be good to go. Yeah, all right, let's try again now. So we're adding two libraries. Okay. It's gonna take a little while. Other than that, we're gonna need some new files to set up VMA. So for VMA, we're gonna need a new CPP file. Let's call this VMA. And we're gonna add it to Git. And what should we call this? Failed to remove directory, huh? What the heck is going on here? Very strange. Let's try to reload that. What in the world? That's very weird. I guess I'm just gonna need to delete the whole thing then. Oh well, for whatever reason it cannot actually freaking remove it. Bruh. That's the last problem I want to happen. I can't remove this shit, so. Bruh, I'm dead. Task manager. What's using that folder? Oh my god. Is it maybe Git or some crap? Something gotta be using that. This is very strange. Can you try again? Finally, oh my god. Well, that's insane. Okay, so for VMA, we need vk to include VKMemAlloc. Well, in fact, let me grab the guide right there. So, VMA guide. They have a wiki thing. Let me see, wiki page. Bro, just give me the wiki page. Come on. Bruh, give me please normal search. Vulkan VMA guide. Well, let's just enter this guy. Actually, it's right here. Quick start, I guess. Yeah, this one. Okay. This is the one that I'm talking about. So we basically only need this. It's a header only library though. So you gotta say define VMA implementation here. And include VKMemAlloc. And of course I'm actually doing it in a second file, so I don't add the implementation in the main file. It's already big enough. So yeah. Other than that, we also gonna need some other stuff, some other defines. We're gonna need VMA static Vulkan function 0 and dynamic Vulkan functions 1. Because we're gonna be giving, we don't want to use like the loader functions directly. We're gonna give it our own dynamic Vulkan functions from SDL, the ones that we actually loaded from the dynamic library, basically. So yeah. Other than that, I'm gonna copy these and put them in the main file too. Though this time we're not gonna include the VMA implementation. The VMA implementation should only be included in this one, in one CPP file. But yeah, other than that, we should wait for this to compile. Where it actually reached, it's still cloning STL image apparently. But yeah, for the initialization, this is what we're gonna need. We're gonna create like a VMA allocator. Now, I mean, we could actually allocate ourselves the image ourselves, but it's not gonna be as efficient essentially, and it's also gonna be quite a hard and lengthy process, because like you gotta essentially enumerate all the Vulkan memory regions, like, and then choose which one you want. Like, I mean, if we go to Vulkan Caps viewer here, There we go. If you go to memory, so like you have multiple memory heaps, you have memory heap 0 and memory heap 1. So for example, memory heap 0 actually have 3 memory types. You have memory type 0, memory type 1, and memory type 2. And it have one flag device local bit, which means this is actually VRAM, like actual dedicated memory, dedicated GPU memory. While this one have no flags. And there's also the device size. So this is the size in bytes, I think, of each heap. So this one is probably the system memory, right? The RAM. And this one is the device local bit. This is the actual VRAM, which is 6 gigabytes basically. So the first memory type is just device local, which means it's not accessible from the CPU, from the system. The second one, same thing. The third one though is actually accessible from the CPU, but actually is inside of the VRAM. But this memory type 2 is very limited, like somewhere around 256 megabyte depending on the GPU. But yeah, other than that, we have memory heap 1, which is the actual system memory. There's multiple ones. There's one host cached and one that is not. Okay, so apparently SDL3 image is invalid. Let me go back to my own let me see, hold on. Let's open this GitHub. Kodotaku CMake repo. CMake list real quick. What is the SDL3? SDL3 image. Okay, I see. So the actual real name is SDL3 image, SDL3 image. There's no clear guidelines on the names. If you didn't, like, if you want to figure it out yourself, just check out their own CMake list in GitHub, and yeah, which I already did. And there we go. Okay, let's try to actually compile this now, I think. Okay, where we were here. But yeah, but we don't actually have to deal with this directly if we just use VMA, which is very good actually. Can be updated. Also the database that I actually forgot to mention in the previous video. Here, like, you could find all sorts of GPUs. Like for example here, let's say Samsung or RTX 4070, for example. If you click on that, you could find all sorts of reports from RTX 4070 for even multiple drivers, as you can see, multiple driver versions, and multiple Vulkan API versions, and even multiple like OSs, like there's one here Ubuntu, one Windows, etc. Like you could click on any report, and then you're gonna get like the things that you see here, right? The actual extensions, feature, and properties. For your own device, you could actually see all of it here for another GPU, right? So, and that's very useful if you want to explore the Vulkan properties of other GPUs on other platforms, right? So that's pretty sick. For example, the memory here for this GPU RTX 4070, this is probably 12 gigs, I would guess, but yeah. Anyways, so as you can see right now, we have built that successfully. Perfect. Now let's actually use it. So, where are we gonna do this? I think we could safely do it probably somewhere around. Let's just do it here, I guess. VMA allocator. There we go, VMA allocator. Though we actually want to do it in a std unique PTR, just like we did with the SDL window here. Though this is gonna be a little bit interesting. Allocator, comma decal type, VMA destroy allocator. And there you go. Now let's actually initialize that. So in here we could like add init VMA allocator. What did we actually call it, by the way? We just called it allocator apparently, so fine then. Init allocator. And then we could actually create this function here. So like void init allocator. So the physical device, so VMA allocator creates info, we give it the physical device, we give it the device, we give it the instance. Perfect. But of course you're gonna have a little problem here. And just to cut things short, I figured out the solution. Instead of using VMA allocator, which is actually an alias of VMA allocator T pointer, just use the VMA allocator T directly, because the unique PTR itself is a pointer in some sense. So let's just fix that and come back here and see if this fixes it already. Well, actually, my bad. Let's just say VMA allocator here. VMA allocator. Oops. Right. And let's just do it here. And then we could just reset the allocator. There we go. Function has one parameter. What the? Oh well. There we go. So we basically create the allocator, put it here, and then we reset the the unique pointer with that allocator. And that's basically it. Could this fail? I think it probably could fail. I don't know. Anyways, never mind. So let's try this and make sure it's working. And we have a little problem here. Oh yeah, we still have some other things to add though. Hold on. Okay, let's see. Allocator create info. What we need else? So device, flags, instance, physical device. We're gonna need the Vulkan API version. That's one thing. To the Vulkan version. And what else? We're also gonna need the P Vulkan functions that it's gonna use to like fetch the other functions dynamically. Because we didn't allow it to use the static ones, basically. So for that, we're gonna say Vulkan functions, or like just call it, I guess, functions. And we're just gonna say VMA Vulkan functions. Well, not really. Just give it the VMA. Well, vk get instance proc addr. Oh boy. Well, I think we gotta get it from the instance, right? Get dispatcher dot vk get instance proc addr. I think like that. Okay, cool. And also I think we need the vk get device proc addr is equal to the device get dispatcher vk get device proc addr. Other than that, you should probably be fine. Can we actually do this in line? Let me see. I guess so, maybe. Let's do the same thing here. And we could remove these. And what's up? Add const. And let's go. I think this should work now. And there we go, perfect. So now we're probably creating the VMA allocator successfully. I mean, we could like put a breakpoint here and see what's up with that real quick. Oh, what the? Why it isn't? What? Oh, isn't it being executed? Weird. Let's see. I mean, it is. What the heck? Okay, let me try this then. Bro. Oh, we're using the release version. Oh boy. Alright, so maybe that's why we didn't get a good crash beforehand. Yeah, maybe. Well, I didn't actually notice that we were in release mode. My bad. Also makes sense why it was slower. But anyways. And there we go. Okay, so the VMA allocator here. And as you can see, it's actually being properly initialized, which is cool. It also loaded the other Vulkan functions from the Vulkan functions we gave it, which is perfect. It even fetched its own physical device properties, as you can see, and the other stuff. All right, anyways, let's go to the next step. And by the way, can we actually right now detect the problem with the destructure or whatever? No? Yeah, still nothing. Anyways, we're gonna check that later. Anyway, what else now? Now we could actually go ahead and load the image. So where are we gonna do that? Good question. Let's do that stuff here, I guess. So we're gonna load the image. All right. Assets, textures, assets, images, / screenshot dot png. There we go. So of course include SDL image, so you could actually use this guy. And does this also use SDL get error? I wonder. Doesn't really say much about it. But anyways, if not image, just do it. Let's see if this image is getting loaded. Come on. whoops, fail to upload image. That makes sense because we're not setting the, what is it called? We're not setting that thing properly. So how we can do that? Well, we could go to here, and the working directory, we could set it to the, hold on, let me actually copy the path here. Copy path reference, absolute path, and let's go here, edit. Or honestly, instead of that, we could also, yeah, hold on. I have a better idea, because if I do it this way, I mean, it would work probably. Like if I do it this way, it would work. Just setting the working directory in my IDE. But if for someone else, they have to also set up the IDE, which is not ideal. And apparently it doesn't seem to work either anyways, which is strange. Oh, my bad. Well, I see why it doesn't. Because this is wrong. Asset/images/screenshot.png. Come on. Seems about right. And the image here, as you can see, the width and the height, pitch, and the pixels pointer, which is perfect. The type is ABGR8888, which is cool. All right. Now, obviously, this isn't perfect. We have a better way to do this. So let's remove this from here. And let's actually do some fix in the actual CMake. How we're gonna do this. So I'm gonna basically add what is it called? Add absolute path as a macro for assets. Okay. Target compile definitions, project name. So we're going to add it to our executable here. Assets there is equal to CMake current source there /assets/ perfect. And now we could just sync. But hold on. It actually does differ depending on the it does differ depending on the release mode and depending on the build type, yeah. So if it's debug, then we do that. Otherwise, we do this. Interesting. Well, let's just go with it anyways for now. And what's going on? There's something wrong here. Oh, end if. That's what we need. All right, let's try this out. Now we could actually use this assets path macro here. I mean, right now, if I don't actually use it, of course, it's not gonna work because the path is wrong. There we go. But if I actually do something like this, and let's remove this assets thing. It it should work out. It's gonna get concatenated here. At compile time. And there we go. It actually works. Perfect. Though we could probably make this into std, like std file path instead. But honestly, there's no need. Never mind. Oh. Well. Anyways, let's just go straight into actually making a buffer. So creation staging buffer. So let's actually go ahead. So the size of the buffer would be the image width times the image height times 4, because we have 4 components. Though this isn't really, I mean, the image could have a different format, but let's just assume that it is right now 4. Though we could, if we really want to, we could convert it, like, to make sure that it's in a compatible format, basically. Like we could say if image format is not equal to, well, hold on, is this correct? Yeah, it's not. If it's not equal to ABGR888, then we gotta use SDL convert surface format, and we're gonna convert it to that format. And of course, we have to like free the old image. So this is not working for whichever reason. Renamed SDL convert surface. Okay. SDL convert surface. So it's got renamed in SDL3. And there we go. Perfect. Same thing with this guy, I think. SDL destroy surface, apparently. Image. And let's actually make this not read only. And that's basically it. So what's up with this guy right here? We have a little problem. Oh boy. Function has 2 parameters. Okay, let's see. Maybe it got changed. So the image and the format. SDL pixel format. Come on. ABGR. Let's remove that, and there we go. Perfect. And that's basically it. So here we're basically convert image to if needed. Then we create a staging buffer of the size of the image. Usage transfer src. And allocate create info. Usage CPU only. Allocation. Info. Staging buffer allocation. VMA create buffer. So this function has 6 parameters apparently, but it is called with 5 arguments. Let's see. So we got the allocator, the buffer create info, the allocation create info, then the vacate buffer. Vacate buffer, staging buffer. And probably we want it here, I would guess. Staging buffer. Well, need address off, I guess. Now what's up? Cannot convert VMA allocator T to parameter type VMA allocator. Oh boy. Well, I guess dot get to get the raw pointer, yeah. And here vacate buffer create info. Oh, So basically it is expecting the raw C type, but it's getting that instead. Well, how can we fix that? Can we do it like this? No. That's interesting. Buffer create info. How to convert an HPP Vulkan type to C Vulkan type. The get, I don't think there's a get function there. Okay, let's try these. There is no get function, first of all. Other than that, let's try to static cast that then and see if that would work by any chance. Create info. Nah, that doesn't seem to work out. Well, actually, maybe it does. Hold on. I see. Can we say basically became a temporary right there. Raw buffer create info. Now the thing is, VMA is actually using raw API, raw Vulkan API. That's why we need this thing, essentially. Is there anything about the allocation info here? Alright, cool. Why do we even have that though? Weird. Alright, so that's basically it, I think. Add a const. So what's next? Copy image data to staging buffer. Map to data. VMA map memory. Mem copy and map memory. And there we go. So let's see if this works. I'm gonna explain it in a second. What's happening there. Let's see if this works first of all. There's no errors. Are we having the validation layer? Yeah, perfect. We do have the validation layer. So let me explain what's going on so far. So here we're creating a staging buffer. Staging buffer is basically a buffer that is in the GPU VRAM, but it's CPU accessible. Or actually it could be in the CPU, like in the system memory too, but accessible to the GPU. So basically what we use this for is that we're gonna have like a dedicated image memory inside of the VRAM that is only accessible to the GPU. So like it's local to the GPU, it's in the VRAM, in dedicated memory, which is not really accessible from the CPU side, from the, yeah. So how we could actually right now use it, like how we can take the image from RAM to VRAM, is we create this staging buffer, we copy the image data to that buffer, and then we create a command buffer to tell the GPU to go ahead and copy the data from the staging buffer to that dedicated memory image, to that VRAM image. So yeah, pretty much copy image data to staging buffer. Here what we've done basically, we mapped that buffer. So like VMA map memory, allocator.get, right? So, and that mapping of memory would give us a pointer where we could write data into it, right? So here we just use memcopy to copy the image pixels to that buffer, right? And then we nmap it. That's basically it. Next up, we probably want to create the image that is inside of the VRAM, basically. Image type, E2D. Of course, it's a 2D image. It could also be 3D, for example, for... basically, 3D image is just like a stack of 2D images. It could be used for volumetric data, for example. But anyways, the format, of course, it's the right format for the one that we used here. BGRA. Well, actually, this is ABGR. Is this correct? Yeah, it is correct. Perfect. So here, extend cannot convert. Yeah, let's actually convert this. Static cast. Same thing here. Let's convert it. Static cast. And there we go. Next up, MIP levels 1, array layers 1, samples 1. Tiling optimal. And usage here, we actually need transfer DST. I think we have done transfer SRC somewhere, no? Yeah. So notice that the staging buffer, we actually made it transfer SRC because we want to be able to transfer data from it. And here, this image in the VRAM, we made it transfer DST because we want to copy data to it. We want to write to it using transfer operation. We don't need sampled here though. We're actually gonna, after that, we're gonna be copying this image to the swapchain image. So we're gonna need also the e-transfer SRC instead of the sampled here. If we were going to be using this texture for a shader though, we would have needed sampled, but for now we're only using transfer operations, so we need that. Well, image usage, not buffer apparently. Okay, so that's basically it, I guess. Initial layout in the find. And image allocation. And of course, we're going to use VMA to help us allocate memory for it. Raw image create info. Perfect. Perfect, perfect, perfect. VMA create image. And yeah. I think that's probably it. We could put a breakpoint just to make sure everything is correctly laid. No problems. Cool, but like, why the heck it didn't trigger my breakpoint? Okay, let's see what's going on here. Oh, vacate image null. What are you talking about? So maybe then it failed? Huh. Staging buffer is there, for example. But this one, for whatever reason, is not. function similar to VMA create buffer. Well, let's actually see an example from there. Like if we go to here, we could probably find some sort of an example. Or we could just simply ask AI here how to create an image VRAM image using what is it called? VMA. See if I'm missing something here. Allocate info. Do we actually have an allocate info here? There is an allocation create info. Oh no, it's actually using the same one, which is not what we really want here. GPU only. Is that really all? What else? If result not equal to vk is success. Oh, so we could check that out. All right. So if not equal to vk success, then we have a problem. Throw cd runtime error, failed to create image, basically. And yeah, same thing with the other ones. I think this one doesn't return anything, this one does. So if not equal to vk success, then throw a runtime error. Probably same thing here. If not, well, sorry, not that. Let's just say not equal to vk success, then we're gonna throw a runtime error. And that's basically it. And this time, somehow, the image is actually being created. I'm not sure why that failed before. But there we go. It actually works now. Perfect. Perfect. Okay, so right now we actually need to create a little command buffer. Or we could just use one of the command buffers that we already allocated, I think, from the frames. Yeah. We could do that. We just need to make sure to reset it afterwards, I think. So let's go ahead and do that. So let's see if it could figure it out on its own. One time submit. Frame.command buffer begin. Begin info. Okay, what's next? Copy buffer to image. Let's static cast that to in32. Static cast that to. Perfect. Let's see. So we're beginning the command buffer, then we're using the command copy buffer to image. So we're copying from staging buffer to the vk image that we created. And the layout is of course transfer DST optimal DO. Can we actually make this into the initial layout directly? Hold on, before we actually do this, I'm just gonna make sure that's a thing. Or should we actually do it manually? We should. I think we probably need to actually do it manually, but let's see. The validation layer would tell me if that's wrong. So if this doesn't work, then we have to make it back. There we go. So we have an error there. Yep, pretty much no. The only possible values is undefined and pre-initialized. So yeah, I see. So let's actually just keep it as undefined. So that means we have to use our transition image first before we do the copy. No, transition. Let's see. Transition image layout. So we're going to transition our image from undefined e-transfer, no, e-none, pretty much. And here, probably none too. Because this is like we have nothing behind that. Well, anyways. The image layout next is transfer DST optimal, which is good. Transfer right. Yeah, perfect. And finally, we're going to transition, after the copy is done, we're going to transition the image back into transfer SRC. Transfer SRC. Because we're going to be copying it from to the swapchain image, right? So let's see if this works. So transfer DST optimal, e-transfer, transfer right, to transfer SRC optimal, transfer read. Yeah, perfect. And yeah, we're done. I think we could just end the command buffer, yeah. And now we can submit this command buffer. And we do need a fence though, and yeah, we already have a fence, but the problem with fences is that it needs to stay signaled. Oh, actually this is not a problem, yeah, but well, it's actually already signaled, so we cannot use it unless if we reset one. Yeah, we could reset one then. So like fences, what the heck? Oh yeah, we could just get the frame.fence dot reset. Can't we do that? No, apparently not. So let's actually say device.reset fences because it's already signaled by now. And let's set the command buffers and submit. After that, we're gonna wait for that fence, which means we're basically in the CPU, we're gonna wait for this upload in the GPU to finish, this operations to finish. And here I can just say this. And I'm not actually going to reset the fence. Right, so we can stay signaled. Perfect. And of course, let's make sure to reset the command buffer. Oh yeah, also the cleanup. Let's destroy the staging buffer because we don't need it anymore. No fucking way, we don't want to destroy the image, but let's just see what's gonna happen next. Yeah. The other thing is we want to destroy the surface image. What the heck is going on? Okay, so we don't want to destroy this VK image because we're gonna need it. And for the system image that we actually loaded, actually we could remove it even before that. Like we could remove it. In fact, you know what? I have a little idea. Before we wait for the GPU to finish, we could do any work, and here we could just destroy that surface, really, before waiting for it. That crap, but yeah. And that's basically it. Did we actually reset the command buffer or not? I don't think we did, so and that's basically it. A lot of crap is going on there. Alright, let's see if there's any validation errors so far. Hopefully not. I mean, if the logic in my head works, then there should be no problem. No validation errors, but if it does really work, I don't know. One way, well, can we actually check it in RenderDoc? I mean, I don't remember. Or instead of RenderDoc, maybe we could even use nsight. Though, well, let's just try. Let's just see what the heck's gonna happen there anyways. So, build, debug. Let's grab the binary there. Go to Chaco Volcanic, open Explorer. Let's copy the path here. Well, hold on, copy the path. Where's the path? Copy its path. Okay, cool. Let's go to RenderDoc here and see if we can actually, I'm not sure if I could access it from here. Oh boy, there's some problem with RenderDoc here. Oh yeah, I see what's up. Let's actually disable the validation layers real quick. And then a PRT screen to capture a frame. And let's see what we got. But this is not really the image that we actually want. Can we access the other images? I don't think. Yeah. You know what? How about we capture the first frame ever? How about that? There we go. Okay, cool. Lovely. So I captured the first frame, which actually includes those commands, right? Because we actually uploaded the image from the system memory to the VRAM in the first frame. And as you can see, our screenshot is right there. VKCMD copy buffer to image, and the image is right here. So it actually works. Right now, last step is that we actually, first of all, we need to load this image. So let's actually keep it here. VK RAII image. Well, yeah. And now, where is that VK image? Here. Okay. So let's set that image to its right place. But that needs to be optional, right? Hold on a second. This needs to be optional. And we're gonna reset it. or should I say in place? Yeah, in place, but oh, apparently we already have that. I see. So let's call it something else. I don't know. Texture. Let's call it texture. Fine, because it's in the VRAM, so it makes sense to call it texture. Texture dot in place. Device vk image. Perfect. And yeah, so right now we should have a reference to it basically, and it should also be automatically destroyed on application exit. Other than that, let's go to the frame logic, right? Our record command buffer function, and after clearing the color image, so here we transition it to transfer the ST optimal. We have clear color, and then at the same time, since we are already in transfer the ST optimal, which is great, we could actually copy the image, copy the texture, or should I say blit, texture to swapchain image. No need to transition the image layout because it's already in the correct layout here at this point in the command buffer. So let's see if we could figure this out by itself. So here vk image, src image, access to non-static member without an object argument. What the heck are you talking about? I don't know what it's talking about. Anyways, access to non-static member. What? Huh. Oh, this is strange. Oh yeah, because this is static. Let's remove the static from there now. And there we go. Okay, cool. What's next? Here it's trying to get the width and the height of the texture. I see. I don't think we could get that, right? I think we should just store it. Yeah, pretty much. We should just store it. So, okay, sure. Let's go ahead and do that. And so, texture width, comma, and here texture height. What the heck? Why it's having a problem with this? Okay, that seems about right. Or no? Aggregate initialization failed. SCD array. Okay, I'll set 3D. What is the type here? Int 32. That's strange. It should be... Oh, I see why. Because this is an offset 3D. Alrighty, gotcha. So that means we probably still want static cast here. Just not into U in 32T. And maybe then that would solve the issue. What the heck? It's still not. That sucks. Anyways, can we do it this way? Oh my fucking... Okay, let's do this. Simple way, I guess. Let's see the array, VK offset, 3D. So these are the SRC offset, I believe, right? Yes, it is. Or, in fact, we're probably going to use the same. Yeah. Apparently. Well, let's just try this out. Thank you. Well, in fact, here. Offsets. Yeah, so these are like the SRC offsets, let's say. And the other ones are CD array DST offsets. There we go. And let's use them here. Whoops. Well, actually remove this whole thing. And the aggregate initializers in C++ are very confusing to me. Sometimes they work, sometimes they don't. I don't really understand how it works. It's crazy. Crazy, crazy. Anyways, what's next? Add const. Add const. And finally, let's see if this works. If everything went into plan, we should have the image blitted into the window. And I'm not sure what's happening here. Can we actually launch this again? Just see if we can notice anything strange. PRT screen. Okay, let's see what we got. So we have a Blit image here. The input is this texture, which is perfect. But the output is, for whichever reason, this crap. And I think it probably makes sense. This is offset. So I would guess it actually needs to be 0, 0 instead of this crap. No? Yeah. But no, hold on, what? You know what? Let me see the actual documentation of this. How VK CMD Blit image works. Source top left, source bottom right. hold on a second. Am I setting the width and height? I don't think I am. Okay. That's probably the problem here. So let's actually do that. Let's fix that. Well, where is it? Here we go. Okay. Let's fix that. Where's the image? Lloyd image. So here, let's make sure to set that. Texture width is equal to image W, and texture height is equal to image H. I think that's probably the problem here. And there we go. It actually works. Let's go. Though the image looks suspiciously weird. I think it's probably something to do with sRGB crap. I don't know. Maybe. Hold on. Let me see what we have here. What is the format that we actually picked anyways? Unorm. What if it's sRGB instead? Would that even work? I don't think so. Actually it does. There we go. So that's perfect. All right, so we have done it. We have done it. Alrighty, let's go. That's pretty sick. So right now we made a Vulkan application that could basically load an image and essentially just continuously render it into the screen. There we go. Of course, only using a transfer operation so far. So that's pretty sick. Let's go. Let's go. And there is some allocations were not freed before, which makes sense actually. Hold on, what? No, hold on. What is it called? Okay, some allocations were not free before destruction of this memory block. How to actually allocate stuff? Hold on. I mean, deallocate stuff. Destroy buffer. VMA destroy image. It's probably what they're looking for here. Yeah, probably. So maybe instead of vacate RAI image, maybe I should try just vacate image and then manually do that thing. Manually handle the destruction, which sucks. But, or you know what? Hello Lucas Sanguino, welcome to the live stream. ¿Qué tal? What does that means? Which language is that? Instead of this, maybe what we could actually do is std unique ptr. Well, hold on a second. Oh no, that's actually quite interesting. It needs the buffer and the allocation. All right. I see. So let's keep that texture, just not the vacate RAI one. But we also need to keep up with the vacate image well, sorry, VK allocation, well, VMA allocation, yeah. Need to keep track of that. What else? I think that's basically it. The buffered, yeah, that's pretty much it. We need to keep track of that too. And then, so where does texture being used again? Texture.inplace. There we go. Now the overloads accept 2 arguments. Well, if that's the case, can we just in fact remove that thing? Like texture, we don't need std optional anymore. Yeah. Now let's see where we're using that thing again. Let's see. Texture in place. Now we could just say texture is equal to vk image. Well. And texture allocation is equal to image allocation. Okay, and in the destruction code, we're going to device wait idle, and then we're going to VMA destroy image. And it needs quite a few things. It needs the actual texture and the allocation. And there we go. Now if we run this, we shouldn't have that problem anymore. You cannot reference an operand type. Okay, makes sense. What about now? We're basically turning that into a vk image, and then, but yeah, there we go. I think that's probably it for this live stream. That was cool. Oh God, what the heck is going on here? Yo. Why is showing up all these changes? This is stupid. External. Oh. Oh. Okay, that's weird. Let's add this external into the git ignore. Apparently some library is probably pulling off this this stuff, which sucks, but anyways. Now why it's still showing these changes here now? What? Bruh. Weird. Update git ignore. Let's try updating git ignore first and see if that solves the issue. It's still showing all the freaking images. Come on. Sorry, all the files. That's wild. What the heck? Let's try to rerun cline here. See if that's an issue of that. Updating. Oh, I could actually say refresh here. But it still sucks. What the heck? Bruh. I'm very confused right now. Well, you know what? I guess I'm gonna handle this off stream. Anyway, so that was it, guys, for this stream. Thank you all for watching, and see ya in the next one. Goodbye, everyone.